Hi class, this is Professor Kim Nelson with the Fashion Institute of Technology Jewelry Design Program. This is a continuing tutorial on our techniques for drawing in Rhino portion of the class. This tutorial will be dealing primarily with the basic mathematics and geometry behind Rhino curves. This is a review of what we discussed in class. You do not need to follow along on your own systems unless any of this is unclear, in which case I do recommend that you do so. Okay, you're going to start by drawing some curves and circles. Draw a line, single line segment, using grid snap. I'm going to draw a series of circles. These will be 4mm circles. Okay. And behind every Rhino curve object, there is a mathematical equation, as we've discussed. You can see this math more directly when you come into the Edit menu and you turn on the control points. And right now, this is what the math of our objects look like. Okay? A straight line is a first-degree curve with 2 control points. Every curve in Rhino has 2 aspects. It has degree of curvature and control points. The degree of curvature mainly depicts whether the line will be a straight line or a curved line, and then beyond that dictates the area of influence of the control points within that curve. This will make more sense as we go through this tutorial. I want to rebuild a number of these items so that I can show you how the control points interact with the math of the curve. So I'm going to be using the rebuild command from the edit menu. Select the curve I want to rebuild. I'm going to make these lines have an 11-point count. I'll keep this first one at a first-degree curve. I'll make this one a second-degree curve. Notice that in parentheses, you have the current point count and degree. Also remember from class that the point count has to always be at least 1 point higher than the degree of the curvature. So a 1-degree curve, first-degree curve, has to have at least 2 control points. Second-degree curve, at least 3. Third degree of at least 4. Fourth degree, at least 5 control points, etc. Since we're using 11 control points, we're well in the clear. And actually, I am going to I would like to have a 5th degree, so I'm going to actually borrow this curve, bring it down to here, and then rebuild it. Control points 5th degree. And I'll move all of these up one. The red curves you see in the background are just reference curves. Excuse me. They'll make it easier for you to see the changes in the curves as I work with them. Coming over to our circles. If you want to see what the current math of a curve is, there are 2 choices. In most Rhino training classes, they'll tell you to type in the word what and hit enter. select the object, and it'll tell you. It's on the layer, it's a valid curve, and well, in Rhino 4, it tells you what the math of the curve is. They don't here. So I never use that method anyway. I was just showing it to you. So much for that. The way I find the math on a curve is I rebuild it. Okay. Now I don't have to actually rebuild. I can just hit cancel. But by looking in the parentheses, I can see very clearly what the math of the curve is. Okay. All circles in Rhino are by default second degree curves with 8 points. We're going to rebuild ours to have 16 points. When you rebuild a circle, guys, it's important that your control points be a divisible of 4, or a multiple of 4. Okay, that's so that you can maintain a point at each one of the axes, and then increase the number of points in between the axes. So 16 is a good one. 20 is also good. We'll use 16. So change the control point count to 16 and increase the curvature to 3. You'll notice it still looks very much like a circle. It is no longer mathematically a circle. But to the human eye, you're not going to see a difference. Okay, so I now have the native second degree, third degree, fourth degree, fifth degree. And for fun here at the bottom, instead of doing a 6th degree curve, I'll actually do a 1st degree curve. Alright. So, I'm going to come in and start talking more in depth. This is a 1st degree curve. Alright? Oh, sorry. Being a 1st degree curve means that each point is completely independent from its neighbors. So moving one point will not impact any of the neighboring points. But that also means that any 1st degree curve is either a single straight line, if there are only 2 points, or a polyline, a segment of lines connected together, each one being a straight line segment. 2nd degree curves mean that when you move the control point, the influence of that moved control point will extend through one point adjacent on each side, but will not reach as far as the next bracket of points. I want to take a minute here and just see. Yes. This is a graphical representation of the curvature of that curve. And you can see that it extends just beyond these bracketed points and then stops. You can also see a hard corner, a hard transition. 2nd degree curves are always a segment of a circle. They're always made up of arcs. Arcs have what you might want to consider like mathematical pinchers. They're held in position to keep that mathematical purity, and that means that they have kinks in them, invisible kinks that you will not interact with unless you do specific kinds of editing on the curve. Third degree curve. You can see that it lifts that curve even farther away from those first bracketed points. But the influence mathematically will reach out to the next set of points. So this would be 0.1 for your third degree curve, 0.2, 0.3. Okay? What that I want you to understand is that the actual name of the degree of the curve, first degree curve, means the mathematical influence goes 1 point. And that's the point you're adjusting. Second degree curve, the influence goes 2 points. The curve you're adjusting and a point on either side. Third degree curve, influence is the point you adjust, and 2 points on either side. So, to show that, I'm going to apply a curvature graph to this. Curvature graph is just an analysis tool that allows you to visualize the curvature. And now that I've done that, you can see 2 things. You can see that that curvature graph reaches all the way to those next points. You can also see that this jagged kind of hard pinion here is gone. It's a smooth curve, but the influence reaches to here and here. Fourth degree curve. Line reaches even farther away from the base curve. Alright? And while it looks like the influence reaches only as far as here, it does not. It continues. The influence mathematically goes all the way to the next point. Point 1, 2, 3, and 4. Oh, can you... I'll hold on just 1 second. Tutorial. Can you talk to me in like 15, 20 minutes? Okay? Okay. Excuse me. Sorry about that. So I'm going to turn on the curvature graph so that you can see that influence. And it's hard to see at that display scale. So I'll increase the scale. And you can see how much farther out it reaches. Fifth degree. Reaches well beyond this curve and mathematically farther still. 0.1, 2, 3, 4, 5. The math reaches almost all the way, the mathematical influence almost all the way to the end of the curve. I will add this and show the degree of curvature. So you can see that the math does indeed reach all the way to here. Okay? What does that mean? I mean, it's interesting to see, I hope. But what does it mean in terms of actual modeling? What it means is that the higher the degree of curvature, the smoother your curve is going to be, because each curve extends its influence farther, each point extends its influence farther and farther along the curve, that the curvature becomes smoother and smoother and smoother. The trade-off for that is you have less precise control over the curve. I'll show you what I mean. I'm going to move each one of these curves the same way as I did the first one. Going to select every other point. Now realize that as I'm doing this, just because it's always good to learn as much as you can with each thing I'm doing, the selection method I'm using is the click to select method. Using my left mouse button, I click, and then to add to that selection, I hold down the Shift button. If I were not holding down the Shift button, the next time I left clicked, it would select what I click and deselect everything else. So to prevent that from happening, hold down the Shift key. If you want to remove a point, say you picked one on accident, hold down the Control key while you click that, and it will remove it from the selection. Okay, I'm going to move these all the same distance as I did that top 1 degree curve. Come back in and take a look at the difference. You can see that in the 2nd degree curve, it all moves up away from the base curve, but each point exerts equal influence, of course. Remember, 2nd degree curve is always a segment of an arc. But you still have quite a bit of control. Each point, of course, pulls very hard on its own specific radius, just itself, and the point, 1 point away from it, and then beyond that, it has no more influence. 3rd degree curve begins to smooth out. These are no longer portions of a circle. You can feel that hard circular shape. That's not here anymore. This is more organic. And each point exerts less control on the curve. Since the influence is felt farther and farther away, it's not as much of a grip, not as much of a pull in any one point. 4th degree curve, even more obvious. 5th degree curve almost reverts to a straight line. Just for interest, I will show you the curvature graph. Analyze, curve, curvature graph on. You can see the hard kinks on the 2nd degree curve, maintaining those circles. Notice the kink on the 3rd degree. It doesn't affect the line, but you can see it in the math. There are no points or kinks at all in the 4th degree curve or in the 5th degree curve. Okay? So, which one's best? Depends on what you're using it for. All right. Rhino, if you want to draw a circle or a portion of a circle, 2nd degree curve is what you want. If you want to draw straight lines, 1st degree curve is what you want. If you want organic curvature, you need to go 3rd degree or above. Rhino loves the 3rd degree curve. That's what it will, by default, always generate for anything that's not a straight line or a portion of an arc. It likes it because it seems to be a nice balance. It gives you a fair amount of precise control over the curve, and it still gives you relative smoothness. Problem is, as you saw with the mathematical graph, 3rd degree curves can still have kinks. Can still have mathematical hard spots, as it were. The 4th degree curve is the 1st degree of curvature that has none of that. So, while Rhino loves 3rd degree curves, I love 4th degree curves. For my own work, when I'm doing an organic curve, I rebuild it to a 4th degree. Now, if you want to influence a curve, have more control over a curve, but it has a higher degree, the way you do that is you add more points to it. You rebuild it with a higher point count, and that'll give you more control over the curve. Of course, it makes a denser curve and a more cluttered, and in the end of the day, kind of a more difficult to manage curve. So there's a concern that you weigh out each time you rebuild and work with your curves. Going to our circles. First off, notice that the 1st degree one that I did at the end for fun is no longer curved. Because it's a 1st degree curve, it has 16 straight segments, each one separated by an independent control point that is not influenced by any of its neighbors. Going back to the top. control points on. This looks very nice and circular, and it is. But the problem with trying to edit or manipulate a second degree circle is that when you grab a point and move it around, you can see the kink. That's that pinion. That's that mathematical grip that holds the curvature as a perfect circle. Those really get in your way if you try and do smooth point manipulation. Going to the third degree curve, you can see that now as a third degree curve, I can pull on those control points. And I have a smooth object, a smooth curve. Okay, there is still mathematically speaking, can you see all the corners, the hard edges, the hard points? There are still mathematical clamps on this. You don't feel them very much usually, and usually you're fine, but sometimes you will find a kink, usually in the form of really complex geometry in a surface that you want to work with, created by third degree curves. So myself, once again, I prefer working with fourth degree curves for anything that I don't mean to keep as a straight line or a portion of an arc. There are no points anymore in the math. No clamps, no kinks. And the fifth degree curve is smoother still, but it's harder to get really precise control because each point influences so many points to the side of it that you tend to get a softer and softer shape. When you want that, fifth degree curves can be useful. All right. The next thing I want to discuss as far as curve math is the concept of tangency. How you use your understanding of the math behind a rhino curve to create smooth, flowing geometry. I have a straight curve, and I want to create something that runs tangent. Tangent means runs smooth. Something that when I make a surface from it later, there won't be a line or a crease in the surface. I want nice, smooth geometry. How do I ensure that? Well, the best way to ensure that is to understand how Rhino sees a straight segment of line. To show you what I mean, I'm going to draw a free-form curve using an interpolate curve. I'm just going to draw something. I'm going to rebuild it. And here's a tip, guys. I rebuild almost every curve I draw. Right now it's a third degree curve. Told you it would be. Rhino loves third degree curves with 9 control points. 9 control points where it's very light and efficient for Rhino is not going to give me the number of control points I need to really get a hold of this and do what I want to with it. So I'll take it to 15. Notice what happens to the curve. The yellow line shows you what it's becoming. The red thing shows you when Rhino says, hey, 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 what you're doing is going to really change the shape of this. This is important to understand. You increase the curvature, each point has less of its own individual power over the curve. All the points are kind of bleeding into each other. So the higher the degree of curvature, the higher the number of points. If I want this to stay close to what it was as a third degree curve, I'm going to have to nearly double those points. See? There's still going to be a difference. Usually where I've drawn something really severe and radical, the more it breaks from a nice smooth flowing curve, the more it's going to give me a variance. I don't really care about the variance for these purposes. I'm not trying to trace anything, which will be the next tutorial. I'm just trying to give you an example. So that'll work fine for me. Turn on the points. And there you have them. Okay? What I want you to understand is that Rhino sees 3 points in a row. If 3 points line up in a straight line, you will actually get a mathematically straight segment of line. This is still too loose as far as control points. I'm going to rebuild it even higher. By the way, that's how it looked the way Rhino built it with its so few curves, few control points. I'm going to take this up to 23. There we go. To show you what I mean, I'm going to use a point object snap. I'm going to take this point, bring it right onto that point. Now here brings another issue in Rhino. When you put 2 points on top of each other, you're starting to make a corner. You're also starting to make a mess. Don't ever leave it that way because you'll never know which point is which. See? So it becomes difficult. But you can do it for the purposes of what I'm doing, and that is to create a straight segment or tangency. So I'm going to click on it, and then I'm going to move that same point again, but I'm going to hold down ortho. Hold down my shift bar and pull to the side. Okay? If I do that one more time, move it again, holding down the shift bar. There is a segment of line in here that is straight. Do it one more time, and the length of that segment becomes significant enough that you can see do you feel it? There's a straight line, a straight segment mathematically in that curve. Control points on. Going to do it again. But this time, I'm going to draw a straight line. From this point, say to that one. It's just going to be reference geometry. I'm going to pick that point, using my point object snap to select it, my point to move from, click. But my point to move through, I'm going to click on the near object snap. And that'll put it right on that line. I'm going to do the same thing with the next point. See it? Straight line. Tangency, to have a smooth flow, only requires one point in a straight line. Show you what I mean. Draw a line straight off the end of here. And I'll draw a line at a random angle from there. Turn on my control points. This one will be quite easy because the straight line coincides with an ortho direction. So point snap, put it right on top of that point, so I know it's truly in line with it. And push it straight up and click. This becomes a little bit more of a challenge. I need to have some of the straightness going beyond that point. So I'm going to move the point using a mid-object snap. Okay. And now, just like I used for this segment, grab that second control point, point object snap, so I get a hold of that point exactly. Near object snap. There. And you see, if I didn't select that for you to notice it, you can't tell where one curve ends and the other begins. That is a perfectly smooth transition. Same here. If it weren't for this extra piece, you couldn't tell where one ends. In fact, if I use that to trim, you won't be able to tell. So, understanding that math, that idea of what creates a straight segment or tangency, lining points up in a straight direction, is very useful for creating smooth models. Coming to this example. I'm going to rebuild it. Say 5. Oop. Rebuild. Say 5 control points. 4th degree is fine. I grab this point, snap it to the end, ortho, move it straight down. Take this point, snap it to the first point, use ortho, move it straight out. Doesn't really matter what I do with this, but if I want to have a nice smooth arc, I can do that. If I want to know how smooth the arc is, I can come to the Analyze, Curve, turn on my control graph, my curvature graph, increase the scale so I can see it well. And this will give me a nice clear way to mathematically see my curve. As long as I use ortho, folks, when I move this, so it stays in a straight line with the parent curves, you will not be able to see where the seam is on those curves. There is no corner at all. It is mathematically smooth. Okay? The last thing I want to talk about with the math is surfaces. What I want you to understand is that in Rhino, the math of your object, your curve, dictates the math of any surfaces you make from those curves. Remember, all surfaces in Rhino are created from a parent curve or series of parent curves. So, control point for the curve. Control points for the surface. Oh, hang on. Sorry. I just proved my point. Do you remember if this curve is a single curve or a polycurve? It's a polycurve. There are 3 segments joined together. That means it's going to create a polysurface. If I explode that, you will see that the 3 surfaces that comprise that polysurface line up exactly with the 3 curves that made the polycurve I extruded from. And the math, as far as control points are concerned, is identical. See that? So as you're building curves for your drawing, you are building the surfaces. You're mathematically determining what that surfacing is going to be. How elegant, how smooth, how simple, how complex, how adjustable, how rigid it's going to be. So it's important when you're drawing to think of what's behind the curves mathematically, not just the way they look. Oh, by the way, just to demonstrate what I talked about with mathematical smoothness, I'm going to do an EMAP surface analysis on this. Okay? And I challenge you to see a seam. There isn't one. Mathematically, it is a perfectly smooth transition. In jewelry, guys, this is very important because you're going to have these parts prototyped or milled. If there is a mathematical corner in your geometry, there will be. And it's funny because it looks so subtle on your screen you don't even pay attention. But when that part comes out, there will be a very nice crease exactly where there's a crease in your model. Okay? All right. That's enough for math. The next tutorial will be on how to trace. All right? Thanks for your attention, and I'll talk to you next week.